Matter of fact, since we got us a quorum, and I tend to have a hard time shutting up at the end anyway, start a couple minutes early. In fact, I want to start with asking about does anyone have any questions from the homework? Have y'all started on the week 2 assignment yet? Yeah, any questions about it? Okay. What about the reading? Have y'all been reading the chapter ahead? The chapter that we're going to be talking about in class? I really can't impress upon y'all enough how much it helps when y'all come to class with questions. It just makes it easier for me to figure out what it is I need to explain better. Now, since y'all have mastered everything up through 2.1, let's start on 2.2 today. We'll start looking at different kinds of graphs. Because once you tabulate that data and you set up your frequency table, the next thing you're going to want to do is put together a graph that visually represents the data that you've been collecting and analyzing. Now, basically the three we're going to look at, and there's some others we'll look at as well, but the big three are histograms, frequency polygons, and who wants to try and pronounce that third one from 2.2? Close. It's actually pronounced ogive. It sounds like a 70s version of oh snap. It's ogive. Jive talking. No, actually the origin of that word comes from I want to say Renaissance architecture, the early Gothic architecture. Have you ever looked inside of seen pictures inside old cathedrals, how those arches come up in the ceiling of the cathedral and they intersect and meet, and you have the vaulted ceilings with the arches? Those arches are called ogives. Have either of you done any woodworking? Okay, you ever use routers? It's the most common decorative router bit, Roman OG. Well, that derives from the same ogive. So if you know the Roman OG shape, then you know how to pronounce ogive. All right. So, when you're constructing a graph, obviously the first thing you do is draw and label the x and y axes. And on the x-axis, you label the class boundaries of the frequency distribution for the histogram and the ogive. And you would label the midpoints for the frequency. Okay? Who can tell? Do you remember what the boundaries are? What they compare to? Remember when you set up your frequency distribution? You set up cells or bins that have class limits. right? But the boundaries are the midpoints between the limits. Okay, and if you'll recall, they are there to make explicit that there's no gap between these two. Any data that would have fallen between 3 and 4 will have been rounded to either 3 or 4. So the boundary would be 3.5. If we were setting up a boundary, setting up a graph on this one, assuming we're going to do either a histogram or an ogive, then we would label our boundaries. Do you remember how to calculate the midpoint on these? The sum of the boundary, the sum of the limits divided by 2. So in this case, it would be 5. Here it's 9 and 7 is 16. That would be 8. Have you spotted the error I put in when I set up these class limits? Well, this is not the same width. This one is 0 to 3. What would be the class width here? It would be 4. What would this class width be? That would be 3. These have to be all have to be the same width. So if 3 is the upper boundary, the upper limit, and the lower limit should be 1. Okay? But that would still leave a midpoint of 3 plus 1 is 4 divided by 2 equals 2. So if we were going to do a what do we call a line graph? I just call it a line graph. Frequency polygon, thank you. If we're going to do a frequency polygon, then we would label our midpoints. 2, 5, 8. And then you plot the frequencies in each class, draw your vertical bars, whatever. Instead of talking about this in the abstract like this, let's work through example 2.4. We're going to construct a histogram of this frequency table. And you remember that this, right here under example 2.4 at the bottom of page 57, is called a frequency table. So, the first thing we do is we see our class bound. We're going to plot a histogram. So we will mark our x-axis and our y-axis, and then we'll mark our class boundaries on our x-axis. That means we're going to go, get the book up here so I don't have to keep walking back. 99.5. 104.5, 109.5, 114.5, 119.5, 124.5, and 129.5. Those are our class boundaries. And if we look at our data, we can see that they range from a low of 1 to a high of 18. So, go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. That's step one. We have drawn and labeled our X and Y axes. Now, we'll take the frequency of each class and draw a bar graph in it. So in 99.5 to 104.5, we have 2. That means from here to here, that's our first bar. In the next one, we have 8. Which would be here. Next, we go all the way up to 18, 15, 16, 17, 18. Hey, you got some homework for me? Okay, after 18, the next one will be 13. And the next one will be 7, which is going to be right here. And then we've got a pair of 1s. Oh, I didn't draw the last boundary, which is 134.5. And we can shade them in to make it look better. That is one histogram. Yeah, do you have the sign-in sheet too? Okay. And did you have any questions from homework? Okay. Now, we do this, when we set this up, I drew in the boundaries. But this is always important. When you're doing a graph, label your boundaries. Including units, if they are applicable. Now here, what is this? What units would this be? Would each one of these numbers be? What do they represent? They represent the number of cities that had the record high temperature, and how many cities had that record high temperature. So they're not really they're unitless numbers. It's just frequency. All right. Now, Let's use the same data. And in fact, we'll use the same graph. And we will plot two graphs, one on the other, just so you can see the relationship between them. But this time, let's plot a frequency polygon. Okay? Now, and I think I told you just a minute ago. This is basically what you would, if you're working on a spreadsheet, it will be a line graph. Okay? But the first thing we got to do, because we're going to do a frequency polygon, is we're going to plot the midpoints of each one of these cells or classes. So, what's the midpoint from 99.5 to 104.5? Yep, get out your calculators. We got 99.5 plus 104.5 equals 204, divide by 2, 102. Next one, between 104.5 and 109.5. $107. What do we get between 109 and 114.5 each? $112. Okay, someone work on this one. $114.5 to $119.5. And here, $122. All right, got two more to go. $131. $132. Okay. Now, to plot our frequency polygon. What's a polygon? It's just a shape with multiple straight sides. So what we're going to do is here we've got 2. We plot 2. We put a dot, plot a point at the midpoint of 102, right there. And here we plot a point at 8 over 107. And we plot those data points at each midpoint. And then plot our frequency. Draw straight lines from point to point. And technically, since we have 0 above and below, you could add these. All right. And that's already getting messy. But now let's talk about this ogive. The ogive is actually just a special application of a frequency polygon. The difference is that when you plot your frequency, instead of plotting it discretely in each class, you plot it cumulatively for each class. So, what does that mean? Let's go over here and let's look at our data. Let's get our data back up here where we can look at it. We've got classes. Our classes are 99.5 to 104.5, 104.5 to 109.5, 109.5 to 114.5, 114.5 to 119.5, 119.5 to 124.5, 124.5 to 129.5, and I'm being remiss and not putting the little degree symbols there, but these are degrees Fahrenheit, remember. And then finally 129.5 to 134.5. Degrees Fahrenheit. Now, in the first one, okay, these are our boundaries. We've got midpoints of 102, 107, 112, 117, 122, 127, and 132. And our data are our frequencies, I should say. 2, 8, 18, 13, 7, 1, and 1. Okay, now, in order to plot cumulative data, you just keep a running total. As you progress to increasing frequency. If we start off at less than 99.5, we have degrees. We have 0. As we go from 99.5 to the next boundary, we get to 104.5. And remember, these are boundaries. These are not the class limits. Okay? That means that we won't have anything that's equal to 104.5. It will be less than 104.5 because it would have been rounded to fit within the class boundaries before we started tabulating the frequencies. And as long as we're less than that, then we have a cumulative frequency of 2. In all of our data, 2 of them are less than 104.5. Next, we go to less than 109.5. And how many do we have? 8 plus the others would be 10. Go to less than 114.5, and we have up to that point another 18, so we are up to 28. Okay, next we add 13 to that. That brings us to 41. And to that we add 7, which brings us to 48. And we add 1, which gives us 49. And we add 1 more, and that gives us 50. Okay? What's the first thing we notice if we look at our original graph? Can we plot this new cumulative frequency data on this graph? If we do, we're going to have to add 30 more. We're going to have to add a third more than that again on top. So instead, let's come over here and add a secondary axis. I don't know if the book says, if that's what the book says we're going to do, but this is, I promise you, if you use a spreadsheet or graphing software, you will find that it will offer you chances at times to use a secondary y-axis. This is why. Because if you want to plot this, and they're particularly useful when you're plotting actual data on one side, but on the other side you're plotting percentages or something. So here we're going to go 10, 20, 30, 40, and 50. Now, where do we plot this first one? At less than 99.5, we have 0. So, at 99.5, we put a 0. And I'm going to see if I've got another color marker to use here. Change that to a 0. Now, the next one is at less than 104.5, we have 2. So I'm going to come over here to 104.5. And there's my 2. Now remember, I'm now using this scale, so this would be actually too high. Two would be about, let's see, 2, 4, 6. It's going to be close enough, I guess. Next one, 109.5. Less than 109.5, we've got 10. So now we're coming over here to 10. Less than 114.5, we have 28. That's going to be about right here. Less than 119.5, we have 41, which is going to bring us up to about right here. Now we've got 48. It's going to bring us to about right here. 49, which will put us here, and 50, which puts us here. But you'll notice that I'm drawing each of these data points at the upper boundary limit of each class, not at the midpoint. Because in this cumulative data, it represents everything from that point down. Now we plot this. And do you see why it's called an ogive? You missed that part of the lecture. Ogive is how you pronounce that, O-G-I-V-E. It's from, I don't know, Renaissance, it's early Gothic architecture. And I explained it to them that if you've ever seen inside a cathedral where they have those vaulted ceilings, where they have those arches that come up and meet and intersect, and they have the vaulted areas between them, those arches are called ogives. If you've ever done woodworking and you've used a router, then you know that curvy shaped bit is called a Roman ogee. Okay, well, now you do. Anyway, this is called an ogive graph. And that's where the word comes from. It's from that Gothic architecture. Now, so yeah, this is what you use anytime you're going to plot cumulative data instead of discrete, point for point data. So, now I think this came up, and I mentioned it in passing earlier. Am I going to need this data back up again? No, it doesn't look like it. They're going to give us new data. Oh, yay. Because you never write enough data tables, right? I'm going to look at relative frequencies. What do you think relative frequency is? And why might we use it? My back is turned. You can look in the book. Right. Basically, think of percentages. And if you'll recall, I told you, when I talk about a percentage, I think in terms of relative abundance, or the ratio, what they call relative frequency. If we have 24 points out of a possible 100 points, then I think of that as 24 divided by 100 equals 0.24, which is, in my thinking, that means 24%. Technically speaking, in order for that to actually be written as a percent, you would have to multiply it times 100, and it would give you 24%. Okay? In my thinking, I generally just skip that last step, and I just think of the 0.24 as 24%. What if we wanted to do comparisons? The example they use here is they want to compare age distribution of adults in Erie, Pennsylvania with those in Philadelphia. All right? Well, if we just plot the raw data, the actual frequencies, then in Pennsylvania and Philadelphia, they have like 1.5 million people. So we're going to be looking at, well, there are 200,000 here and 20,000 here and 50,000 here and 100,000 in this group. Then we go over to Erie, Pennsylvania, where the total population is only 100,000. Well, now in this group we've got here, and in this group we've got here, and in this group we've got here. You see, because here we're talking about 10,000 is here. Well, in Erie, that same number might work out to be, 900 or 1,200. Well, compared to 10,000, it's going to be down at the axis. Now, there's a couple of ways you can deal with that. Sometimes you can plot data logarithmically. So instead of having this as a linear axis, where you go, you can plot that as a logarithmic axis, which would mean you don't start at 0, you start at 1,000, you go to 10,000, and then instead of 20, you go to 100,000, and instead of here, you go to 1,000,000, and you just keep going up logarithmically. And of course, you never get to 0, because 0, what's a log of 0? It's like infinity or something. It's undefined, it blows up. It comes back error on your spreadsheet. How many of you know what NaN stands for? You ever see NaN come back from your computer? Maybe from a compiler error? No? Okay, well, if you ever do, it means not a number. It's what they used to say before they started saying ERR, error. All right. Well, the point is that sometimes when two different populations are greatly different and you want to do a comparison, you just can't really do a comparison with straight linear numbers because the scales are just too diverse. You get no visual information in the smaller one because it's all smushed down against the lower axis. That's when you would use relative frequency. When they want to So let's start with our data. Our class boundaries are, these are the number of miles run by 20 randomly selected runners in a given week. Okay? Well, our first class boundary is 5.5 to 10.5 miles. Because some people are just stupid. I mean, seriously, if I needed... I do not understand why anyone would run. If I wanted to run, I wouldn't have learned to shoot. It's as simple as that. 10.5 to 15.5 miles. 15.5 to 25, which is what I said, but not what I meant. 20.5, not the same. 20.5 to 25.5. I'm guessing 30 point, yep. And that gives us a total up to 40.5. I'm abbreviating miles MI instead of just M so as not to confuse it with meters. Now these are our class boundaries. Real quick, what would the, for you, oh, I forgot your name. I forgot your name, sorry. Jordan, thank you. These are the class boundaries. What would the class limits be in each case? No, the class limits, not as opposed to the boundaries. Class limit for the first one be 6 to 10. Remember, you put the boundaries between the class limits to make sure that you explicitly confirm that there's no data that falls between the two classes. This one goes from 6 to 10. This one goes, what's 10.5 up a half? Would be 11 to 15, 16 to 20. See, these are the class limits. Do you remember now the distinction between the limits and the boundaries and the reason for it? Okay. It's important to remember. And it's important to remember why. Because especially when you're talking about miles, these are what? What kind of variables are these? These are not discrete variables, they're continuous variables. So it's very possible for somebody to have run 10.8 miles. Well, if these are your class boundaries, 10.8 falls between 10 and 11, and it would not actually land in either of these classes. So you establish the class boundaries to show that no, if it came in if someone ran 10.8, it got rounded up to 11. Right? Now, we're also going to need the midpoints. So I'm going to jump ahead here. Plot the midpoints for each of these. What's the midpoint of that first class? Eight. $13, 18, 23, 28. Seeing this pattern here? 33, 38. Just add 5 to each. Or add the class width to each to the first. Add for every once you've calculated the first midpoint, you add the class width to that and each successively to get each midpoint. Now, What are our frequencies? I've got to back up a page. And what does this number actually mean? The number of runners. In this one, we got the first class gives a frequency of 1, then 2, 3, and 5. 4, 3, and 2. That gives us a total number of runners of 5, 10, 15, 20. And y'all are breaking a cardinal rule, trusting me to do arithmetic in my head. In this case, I've got 5 here, 5 here, 5 here, and 5 here. 5, 10, 15, and 20. So, now we calculate our relative frequencies. What's the relative frequency of the first class? One runner out of how many total? Out of 20. So it has a relative frequency of 5% or 0.05. The next one has 2 runners. Well, I can double 0.05. Or specifically, that would be 2 divided by 20, which is 0.1. The next one is 3 divided by 20, which I'm not going to try to do in my head. But 3 out of 20, that gives us, actually we could have done that in our head. Another 5%, or 0.15. Now, someone want to take a crack at 5 out of 20? 0.25. 4 out of 20 would be 0.4. What's 4 divided by 20? Yeah, not 0.4. 0.2. See, I told you don't trust me to do arithmetic in my head. 4 divided by 20 is 0.2. 3, we already did. And 2, we already did. And if we add those up, it should equal, 1, or 100%, yeah. So let's confirm that. And they equal 1. Now, one last column we want to set up here. Cumulative relative frequency. We're going to start at less than 5.5 will be 0. Right? Next one will be less than 10.5, less than 15.5, less than 20.5, less than 25.5, less than 30.5, less than 35.5, and less than 40.5. Okay, less than 10.5, 0.05. Less than 15.5, add 0.1 to this. We get 0.15. Less than 20.5, we add 0.15 to that, and we end up with 0.30. For 25.5, we add 0.25. That brings us up to 0.55. For less than 30.5, we add 0.2, which brings us to 0.75. For less than 35.5, we add another 0.15, which brings us up to 0.90. And then to that, we add 10.1, and that gives us 1.00 for our cumulative relative frequencies. And then from that data, we could plot the different types of graphs that we've just talked about. Now, one more thing I want to go over today. Real quick. And we'll talk about more of this on Friday, but I wanted to real quick look at these on page 64. I want to talk about these different shapes of graphs. Whether we're talking about histograms or frequency polygons. You've all heard of the bell curve, right? Well, look at that first histogram. It's figure 2.7. You see that? There's a bell-shaped distribution. Okay, you're going to see that a lot. That's going to be called a normal distribution whenever those vertical bars become smaller and smaller in width. In the limit, it would be in the continuous limit of those delta x, the width of those bars, and the limit that they approach 0, that becomes the normal Bell distribution. The normal distribution or the Gaussian distribution. But it's not the only shape you're going to run into. And believe it or not, the Gaussian or normal distribution is not the only continuous distribution you would run into. Look at shape B. What does that look like to you? If you were just plotting a function f of x, that would be a constant. Well, in this case, it's called uniform. If you look at C and D, you see what's called the J shape and the reverse J shape. Okay? And that reverse J shape is one that you're going to see again. I don't know if we're going to actually talk about it, but there's one of the types of graphs that we might talk about, we may cover, is the Pareto graph. Pareto, P-A-R-E-T-O. And you will find that the Pareto is always a reverse J shape, or a uniform, or somewhere between the two. E and F are right skewed and left skewed. And this is one that can confuse a lot of people. We'll forget about the bars and we'll just talk about continuous, just a regular distribution curve. That's your normal Bell distribution. You can also have one that does this, or you can have one that does this. Now, which one of those is left skewed and which one is right skewed between the blue and the green? Green is left skewed, blue is right skewed. And that seems backwards to a lot of people. Okay? So if it seems backwards to you, just remember it's backwards. But here's the thinking. To say this one is skewed would be, I took this red one and I smeared all of this data out to the right. Okay? And that's literally what happens to get this shape. Is you get a disproportionate or an abnormal percentage of the total distribution pushed off to this side. So it becomes right skewed. A left skewed is just the opposite. A disproportionate amount of this population is pushed down here and builds up over here to the left, leaving less of it prominent over here to the right. That's what makes it left skewed. So remember, the skew is always in the direction of the tail. Okay? Now, the last two are bimodal and U-shaped. You'll see those. So let me ask you, what is the difference between J-shaped, reverse J-shaped, right skewed, and left skewed? What's the difference? When the maximum, when the highest value is on one extreme or the other, is at one end of the range or the other, then that is either J-shaped or reverse J-shaped. If the peak, if the highest value is not at the edge of the range limit, then it's either left skewed or right skewed. Similarly, you find the same kind of distinction made between bimodal and U-shaped. Bimodal means just that. You have two distinct peaks. Okay? But if those peaks are pushed all the way to the extent of the range limit, then it's a U-shape. Because really at that point, you don't know that that's the peak. You know, for all you know, if you kept looking at data further out, you might find that the peak is even further to the left or right than. But that's the difference, is when the maximum is at the end of the range, then it's either J-shaped, reverse J-shaped, or U-shaped. When the maximum values are somewhere inside within the range that you're looking at, then it's either going to be bell-shaped, left skewed, right skewed, or multimodal, bimodal here. You start analyzing things like atomic structure, and you'll find very quickly that you can have more than two modes. You can have multimodal, polymodal, but I don't think we're going to fool with any of that. But so I told you I wouldn't shut up in time. Class is over. 3 minutes ago. I will see y'all on Friday.